her PhD at MIT with me in 2020. And then she did a postdoc at Berkeley, and now she's a professor. And I'm excited to hear about why everything is so hard. Thanks.
Can you guys hear me? All right, great. So I'm going to try and explain, why everything is so hard in life, just in general. More specifically, the plan for today is to give a reminder of the motivation for fine-grained complexity, to give a reminder of the general reduction technique for fine-grained complexity. My understanding is Virginia has given her introductory talk before, so I'm going to basically give 2 slides from that for people who weren't at the previous workshops. Then I'm going to talk about hard problems and specifically sort of orient towards ones that seem relevant to this area. And then I'm going to go over a couple of small, classic or reductions. So, the big goal for today is to define a bunch of hardness reductions, hardness assumptions, and then give you a sense of what those techniques look like in case you want to show some problem is hard. So what is the motivation for fine-grained complexity? Nobody would consider an n to the 100-time algorithm to be efficient. And in fact, n squared is inefficient for sufficiently large sizes. In fact, we were just hearing about how n log n is sometimes enough to make your clients very sad. So on the other hand, we have a bunch of problems where we haven't improved over their polynomial time in decades. So all pairs shortest path, there have been many improvements, but there's no algorithm that runs in n to the 2.99. Longest common subsequence, we have an n squared algorithm, and there have been many improvements, but none of them have improved over this 2 in the exponent. Diameter in sparse graphs similarly has this property of being n squared hard, but not having improvement, and there are many more. And so, a question, yes?
So you say 199, there's an algorithm for 1999?
No, there's no this is there's no epsilon, no constant epsilon greater than 0, such that there's an n squared, the 2 minus epsilon algorithm. Simply, using this as a demonstration. Yeah, this isn't a case of something really funky happening with a matrix multiplication constant. This is just there's n squared is the best we can do, up to subpolynomial factors. There are, log savings and things like that, but not polynomial savings. So we'd like to understand why we're stuck. And we're stuck on lots of problems from many different sub-areas of CS. And we'd like to understand if we're stuck for the same reason. And the way we address this is by coming up with various problems that we understand to be hard and trying to give reductions between them. So we're trying to give a shared explanation of why everything's hard. In an ideal world, we'd have one problem that would explain everything. We'd be you can't solve satisfiability faster than roughly 2 to the n time, and that explains why every single problem we've ever seen is as hard as it is. Now, unfortunately, this isn't the world we live in, and so there's a proliferation of a bunch of problems that we understand to be hard and the relationships between them, and you're sort of building up a reduction graph. So, what do fine-grained reductions look like? Super easy warm-up. You've got a problem A on input size n, and it requires O tilde A of n time. So, omega, excuse me. So the tilde here is ignoring subpolynomial factors. So, log n, log squared n. And you've got some problem B that can be solved. You can solve A by making a call to problem B that's also on input size n. So this is sort of the easiest case. You're simply rewriting your input and then making a call. And as a result, B has to require the same amount of time as A. So this is the really simple case. What is the more general case? So A is AB reducible to B if for every epsilon greater than 0, there exists some delta greater than 0, and there's an algorithm that runs a little bit faster than this A of n time. And so this A of n time is intuitively whatever the best time we have for our problem A. And that transforms A into a bunch of instances of B. And then we're going to want to use all these instances of B to solve A. And there's two conditions we need, right? So one is that producing all these instances doesn't take too long. Like if we, sort of take longer than A of n time, we're not learning anything. So we have some sort of efficient way to perform, to create these instances of size B. And also the total running time on all these instances of size B is small. Like, so why do we care about this? Because this means if there's an algorithm for B that runs in not B of n time, but B of n to the 1 minus epsilon time, then there's an algorithm for A that runs in A of n to the 1 minus delta time. So this is the general plan for reductions. Making many calls is a pretty common thing we do, not so much like carp reduction style.
They're adaptive.
Yes, and they can be adaptive. You can respond to an earlier call to B to determine what your later calls are going to be. So in fine-grained complexity, we mostly focus on three central problems. I'm going to define them, and then I'm going to get into defining a bunch of problems that are probably mostly relevant for you guys. So threesome, in fact, is one that probably will show up for you guys. So what is that? You're given a set S of n numbers, and the question is, are there three numbers, A, B, and C, that sum to 0? You can, as folklore, you can treat these numbers as being in the range of negative n cubed to n cubed. There's an easy O of n squared time algorithm, and there have been many improvements. Even over the real numbers, there are improvements over n squared, but none of these improvements have saved anything like a constant in the exponent. So yeah, folklore, you can assume this is in a range from negative n cubed to n cubed. And the conjecture is that threesome on n integers requires n squared minus little o of 1 time. So that is, we can have these subpolynomial savings, but we can't have anything more. All right, what is orthogonal vectors? So here, you're given a set S of n vectors in 0, 1 to the d for some dimension d. And here, think of d as being like log squared n. In fact, if you end up caring, you can do anything that's just a little bit larger than log n. It needs to be like larger than log n, but if you don't care too much, you can just think of it as log squared. And the question is, are there u and v that have a dot product of 0? There's an easy algorithm where you just dot product all your vectors together. The best known is from Abood Williams and you in 2015. And it gets a savings that depends on exactly what your dimension is. And the conjecture here is that orthogonal vectors on n vectors requires n squared minus little o of 1 time. And in fact, this is implied by a hypothesis that relates to the running time of SAT called Seth, the strong exponential time hypothesis. I'm not going to define that today, so I'll just leave it as a fun fact for the moment. Finally, all pairs shortest paths. So classic problem that we teach in intro algorithms. You're given a weighted graph, and we want to find the distance between every two nodes. There is a long history of improvements to the running time of all pairs shortest paths. And despite that, we don't have any improvement in the exponents. We don't have any algorithm that runs in n to the 2.99 time. We're stuck with n cubed minus something that is subpolynomial. So all pairs shortest paths, the conjecture is that all pairs shortest paths on n nodes with log n length weights requires n cubed minus little o of 1 time. So polynomial sized weights, trying to do all pairs shortest paths that we can't do better than n cubed. Yes.
So what is the lower bound known for in terms of m number of edges?
So there's a lower bound of nm, but it depends on something called the zero K-Clique hypothesis, and it doesn't strictly apply for all values of n and m. It's sort of like a step function. But yeah, like for sparse graphs, there are still some things known about all pair shortest paths. Yeah. That was some work.
The output is n squared. So
Output is.
So now that we've like gone over the sort of intro to fine-grained complexity in general, here are some problems that Nofar talked about. Or was going to, yeah, like, there were too many questions. I asked too many questions about, what what various things were that slowed her down. So I am going to talk about a subset of these, but my goal here is to talk about some of these hypotheses that might come up, and then also some related hypotheses you might have heard of, and then go over some like simple fun reductions to give you a sense of how you might use these to get lower bounds. So we're going to start with Boolean matrix multiplication. So you have Boolean matrices, and the question is, can you like how long does it take to multiply them? So SBMM, as Nofar defined it, you are multiplying these matrices, and you want to know what the output is. And the claim is that you can't do so in linear time in terms of the entries that are 1. And in general, a claim that you can't solve this in linear time in the input size. So I'm going to mention something. So what is the best algorithm, first of all? The best algorithm is using fast matrix multiplication. You take your matrix, and you don't care about the fact that it's Boolean, in fact. We just use fast matrix multiplication. If the output has a value that's greater than 1, then you know your answer is 1. And if it's a 0, then you know it's 0. Combinatorial BMM. So this is the hypothesis that you can't solve this problem in n cubed time, n cubed minus epsilon time. And your immediate reaction might be like, wait a minute, we have several people in this room who have improved over the running time of matrix multiplication. So the key here is there's a notion that is loosely defined, but a loosely defined notion of a combinatorial algorithm where you're not allowed to use fast matrix multiplication. And I say loosely defined because what does it mean to not be using fast matrix multiplication? Well, that's a little soft. But the key reason that I bring this up is because this is useful if you're working in a situation where, in fact, you don't use fast matrix multiplication, right? Like, if in practice, when you're talking to your clients and you're trying to solve these problems, you're not going to be using fast matrix multiplication, you might effectively be limited to this case. So it's sort of it has trade-offs where many people are sort of allergic to it because of its softness. But also, Boolean matrix multiplication is related to the OMV hypothesis by Hensinger, Kringer, Notagani, and Sarakara. And I'm now going to talk about that briefly. So OMV and OUMV, what are these? You take as input, fixed 0, 1 matrix, and you take n updates, and these updates are in the form of 0, 1 vectors. And now, for every update, you need to return basically the Boolean matrix multiplication version of m times v. So here I'm specifying it as, returning the minimum of the value and 1. So the hypothesis here is that this requires n cubed minus little o of 1 time. And there's also OUMV, which is very similar. We have some fixed matrix M, and now our updates are UI and VI from 0, 1 to the n. And after every update, you need to return UI transpose times M times VI. So why am I bringing this up? I'm bringing this up because it seems like in databases, you have dynamic updates, right? So, in dynamic graphs, our updates are adding or deleting edges, but it seems in databases, to my understanding, your updates would be adding or deleting, relations in a table, rows in a table. And you have queries where you need to give answers, notably like your queries over your database. And you can use this to show lower bounds on things like detecting triangles through a single node. And we're now going to work through that example. So from OUMV, we're given this set of updates of vectors. We're given a fixed m, and then we need to return this value. So this green matrix here is m, and what we're going to do is connect ai and bj if ij is a 1. So I'm filling this in row by row. And now that I filled this in row by row, let's say I have some pair of vectors that I'm being given, and I need to determine whether or not ui transpose mvi is at least 1. Well, I can import ui, where I take the ith entry and I connect s to ai if it's a 1. And I can import vi by doing the same, but to this set B. And now, if there's a triangle, it corresponds to the fact that there is, in fact, ui transpose times m times vi is at least 1. So what does this mean for counting triangles in this dynamic setting? Well, every time we're given an update pair, it corresponds to O of n edge updates, right? Like we might need to delete O of n edges, and we might need to add O of n edges back to represent our new edge, to represent our new vector. So that's a total of n squared updates across the whole set of n dynamic updates. And there are O of n queries. So OUMV is conjectured to require n cubed time across n updates. And so the updates must either require omega tilde, so this is ignoring subpolynomial factors in time, or the queries have to require omega tilde n squared time. And this is in fact tight because there exists an algorithm that runs in this time. So if we're counting the number of triangles, what we're going to do is we're not just going to check whether or not there exist triangles, we're going to be tracking the entire count. Every time we add an edge, there's sort of two interesting cases. One is it's between two nodes that aren't S. Here I'm saying AI, BJ, but in fact it would be fine for it to be any two nodes that aren't S. If we simply want to keep our count of triangles updated and current, we only care if we're adding an edge between two nodes where that forms a new triangle, or if we're deleting an edge between two nodes where it was previously a triangle. And in those cases, you either add one or subtract one. And this all takes O of 1 time. So these kinds of updates are super easy. The kind of update that's really annoying is when you have your node S and you're connecting, you're deleting, say, this edge between S and A1. And now there's many possible vertices you need to look at. So across all, other values AI and all BJ, we're going to go through and check whether or not those currently form a triangle if we're deleting an edge, and then we are going to decrement our count for each one, or if we're adding an edge, if we're newly forming a triangle. So for this means we're taking O of n time for each of these. So our queries are O of 1, and our updates are O of n, and this exactly matches the lower bound we got before. Now, I mentioned that instead, it could be the case that every query is taking n squared time. And note that that too should work, right? Like for S, we can simply look at all pairs of other vertices and count whether it's a triangle or not. So we get exactly the tight bound. So I now, before we move on, want to have an aside. And that aside is about the differences between listing, counting, finding a single instance / search, and existence. So listing, when you're, say, listing every single triangle in the graph, is going to be harder than counting, right? Because given a list, you can determine a count. And counting is incomparable, but generally harder than search. It depends on the problem. For many problems, it's you in fact have you can go from existence to search. And existence is definitely easier than all of these. But there's a detail in what I'm saying, which is this. as we were sort of discussing and whatever, as many questions we're asking far, with listing, you give yourself time to list each solution. And this means that even though counting and one instance and existence are in some sense easier than this listing problem, it's possible, and in fact, in many of the cases, this is true. Many of the cases Nofar discussed, it's true. It's the case that listing is linear in its input plus output size, but the counting or giving a single instance or existence version would not be linear in just the input. So if you're entirely paying only attention to the input, listing is harder than these other problems. But if you're looking at input plus output, listing can be easier. So this is sort of the situation and relationship between those problems. Yes?
So generally, do we have a corresponding unique output conjecture to lean on in the case when the output size being large can make listing easier? Like in the Clique case, for example, unique Clique is already as hard as you need, and then you can just forget about the output size being the helper.
Yeah, it's going to depend. For every problem I'm talking about today, it's the case that existence is enough to solve search because you can just subdivide your problem. Most of the fine-grained hypotheses in the ranges we discuss them in. So for example, for the three-sum problem, in the range of negative n cubed to n cubed, the existence problem is just as hard as listing n to the 2.99 solutions. You can do this because there exists an efficient self-reduction. But if there doesn't exist an efficient self-reduction, it's not necessarily clear that listing is just as hard as existence. And whatever, obviously a lot of this also leans on the fact that if you have enough solutions that it starts running into the running time that you're conjecturing is hard, these things start breaking down. Does that answer your question? But yeah, to give you a sense, the K-sum problem in general does not have an efficient self-reduction, but K equals 3, the three-sum problem does. So, yeah. So, reminder of the OMB hypothesis, we're given n by n 0, 1 matrix n, and n vectors, each of length n, and you're given a VI in an online fashion, and then you need to return m times VI immediately. And the conjecture here is basically that there's no fast matrix multiplication that you can lean on. We, in fact, just have to take the sort of naive n cubed time. So, the picture version of this is we're being handed these vectors, and the fun fact is that an average case version of a very related problem is hard. So I'm now going to discuss that and then discuss what I think this might mean for your database results. So what is the parity version of OMV and OUMV? Well, simply, instead of just asking, if a value exists in some sense, right? If a value is greater than 0, greater than 1, or 0, sorry, greater than or equal to 1 or 0, we're now asking for the parity. So the OMV hypothesis implies the parity OMV hypothesis. And if that interests you, I can discuss it offline. But basically, using standard techniques, that this sort of just immediately works. Parity OUMV, no surprise here. Take your vector transpose times your matrix times your vector, and we care not about just if this value is 0 or greater than 0. We care about the exact parity. Well, it turns out that if you're talking about these parity versions, and you just take a uniformly random matrix and a uniformly random vector, this problem is hard from the original OMV hypothesis. So there's some details here, what exact probability do you need to have your success be? But fundamentally, even in the uniform average case, these problems are hard. And I won't show this reduction, but I'm happy to talk about it offline if it interests you. You can show that a bunch of different counting versions of various graph problems are hard. So counting 5-length ST paths is hard. It turns out in Erdos-Renier graphs with random updates, it's not the case any longer that single source triangle counting is hard, but various other graph problems you might be trying to count are hard. And I suspect that these hardness results mean that some of the results that Nofar described won't work if your updates to your database are uniformly random, but many of these will hold for sort of larger subgraphs that you're fundamentally representing. Like basically, a lot of your lower bounds lean on the fact that triangle counting is hard or triangle listing is hard. And here, triangle listing stops being quite as hard on average, but various other forms of counting problems become hard. So Nofar mentioned the triangle, yes?
Those are simple paths, right? Paths where you can.
Yeah, these are counting simple paths of length 5 between two nodes S and T. So triangle hypotheses, Nofar mentioned various versions of these where you can't, in linear time, decide on the existence of a triangle. And the alternate hypothesis is that counting triangles or detecting triangles requires n to the omega time. So you can't decide the existence of triangles in n to the omega minus epsilon time, where omega is the matrix multiplication constant. So, Virginia, you may have heard ask the question, well, like if omega equals 2, like if there exists a fast matrix multiplication algorithm in n squared time, then these hypotheses would be violated. And the answer is yes, but of course, at the moment, we don't have such a fast matrix multiplication. So, new fun fact, triangle counting is in fact hard in Erdos-Renier graphs. So this is from BBB19, Bois and Dessart et al. And they showed that if you're counting k-cliques in an Erdos-Renier graph, if it takes n to the a time with probability something that depends on k, but with sufficiently high probability, if you can do this in random graphs, then there exists an algorithm for counting k-cliques in worst case graphs in time n to the a times some subpolynomial factor. Yes?
What's the degree of the Erdos-Renier here?
P equals 1/2. They have, okay, so their paper, has results for cases where the probability isn't 1/2. It changes various values of these things, but for any constant, you can shift that and make it work. Yes.
I'm just trying to parse it for a second. So these are Las Vegas algorithms that have to always be correct, but their running time is random, and then you need the probability that they're.
Yeah. So what I mean is, like, you're guaranteed your input is coming from this distribution, and then if you both give the correct answer and run in time n to the a with probability at least this, then you can use such an algorithm to solve the worst case problem.
Can the algorithm be wrong sometimes?
Yes, absolutely. Yeah. Like the key sort of advantage and power you get in the average case is that your algorithm can be wrong on sort of non-typical inputs. So the, whatever weird fun fact here is that having an algorithm which is wrong, having an algorithm that's right, 1 minus some, large polylog is enough to get you a correct counting algorithm in the worst case. And so you can think of this as like, even if like you're just doing pretty well on typical inputs, like this isn't even like that atypical, right? Yes.
I think
he's asking is the probability of a distribution or the algorithm, and it is
Oh.
that it's correct only. Yeah.
Yeah, it's both. Like whatever random coins you have and the distribution. So it's okay.
It does not have to be correct algorithm.
Yeah, the algorithm does not have to be correct. The algorithm can be wrong on, this 1 over log n fraction of 1 over log to the 2
I
squared.
suppose it's 1 over log.
Yes, sorry, there's a negative missing here. Here, let me.
Is the runtime also probabilistic?
The running time can be probabilistic, but you need to like be correct with this probability. You need to simultaneously be correct and running quickly. So like you could have an algorithm that runs for a really long time on some percentage of the inputs.
So this probability is for both the correctness and the runtime bound?
Yes. Yes.
Just want to quick comment that this would be an interesting result in the database query. So let's say we generalize this to counting number of answers to a conjunctive query. Is it easy, or can you see a way to kind of generalize that to?
Yeah. So I suspect that this should work. This is sort of why I brought this up. I'm like sufficiently unfamiliar with your area that I can't with like immediate certainty be like, yeah, it's totally just going to work. But it strikes me that with the right model of like what's going on in the database, like obviously one of the issues is it depends. The devil's always in the details. It's going to depend on exactly what we mean by like a random update. Like, are we adding new nodes in addition to changing edges? Like whatever, whatever. There's a lot of details here, but it strikes me as being almost direct. Like I think we should be able to overcome this. And notably, one thing that's nice is like it seems like in a lot of the database results, implicitly we're talking about like k-partite graphs. It's like we're gonna have a random k-partite graph. Now is this hard? And it turns out that using inclusion exclusion, you can just get all the way to Erdős-Rényi graphs anyway. So like a lot of the details that seem like they might be a little ugly, where like, oh, this edge set isn't quite right or something, can be pushed through. And also I have a paper with Virginia and Mina where not just for cliques, but we show that this is true for counting any subgraph. So if it turns out that like for whatever reason, we don't want to talk about triangles or k-cliques, we want to talk about some other kind of graph structure, you can get this worst case to average case. Yes.
So then the probability will depend on the pattern, like the 2 scale changes, k-square changes.
Yeah, like how much you get a blow up depends on the number of edges and the exact shape in some, whatever way. And basically, as long as k is a constant, it's just some polylog. So if you're like okay with success probabilities that need to be 1 minus 1 over some polylog, and you're okay with your running time being blown up by some polylog factor, then you can do this for arbitrary subgraphs in a graph and show that like counting that subgraph in the worst case and counting that subgraph in an Erdős-Rényi graph have a reduction between each other. But yeah, my open problem for the later discussion is going to be like, so it kind of seems like probably all the results work on average. Discuss, Yes.
I have this basic confusion. So in an Erdős-Rényi random graph, it's easy to estimate based on the probability of the Erdős-Rényi distribution the number of k-clicks.
Yes.
An exact computation that is very easy to do. I should know, but I don't know the concentration of this number. But if it's highly concentrated, can't I simply return that estimate and already get an algorithm that runs in time much better than n to the 8?
Yeah, so the key is that it turns out like exact count really matters here. So let me just give an aside. So like the basic idea for a lot of these comes down to the same basic idea about why multiplying matrices is hard on average. If you will permit me sort of random aside here. So let's say we're multiplying some matrices, A and B, and A and B are drawn from some some finite field of a prime, whatever, n by n. So here's what we're going to do. We're going to draw uniformly random x from this, and we're going to draw uniformly random y. And now we're going to ask the following 4 problems. A plus x times b plus y. A plus x times y. X times b plus y. And x times y. And we're going to subtract these and add this. And I claim that this is going to be exactly equal to AB. And this is because AB exists where we want it here. And this is basically just inclusion, exclusion, redux. So each of these problems, individually, looks independently random, right? We've effectively added a random mask on top of whatever our matrix was, or we're just looking at a random matrix to begin with. Obviously, these problems are correlated with each other. And so you need to assume that whatever algorithm is solving this problem has a sufficiently high probability that we're okay union bounding, basically. We need it to be the case that you get the right answer on all of these in order to get the right answer in the final problem. But this is sort of the underlying idea, hidden behind many layers of some horrible polylog number of queries and a bunch of stuff going on. This is sort of the underlying idea of what's going on. And so the exact count ends up being really important because we're effectively going to be adding and subtracting a bunch of counts together. And so if you just get an estimate that's within some reasonable factor, by the end when we're coming out the other side, we're going to have an estimate that's within something very large, and now we can't solve the problem of detecting a clique in the first place.
This was very good.
One more question.
Yes.
How many bits of the output you actually need in this? Is it true that also the parity of this counting problem on random graphs is already hard, or does the reduction not work?
Yeah, the parity works. So there's a really fun paper by Oded where he takes this paper and gives, so BBB19 in fact includes this result. Oded gives a really simple treatment of this, and whatever, if you like fun reductions, I'm happy to send you that paper. It's nice and clean. But yeah, the parity version of this works, and then the parity version continues to work for all subgraphs, regardless of whether they're cliques or not.
Okay, so that gives another explanation why an approximation, as Dan suggested, doesn't work, right?
Yeah.
With the lowest value bit, the approximation won't help you.
Yeah.
Good, thank you.
We don't have analog results for detection, right? Of course, we will need to set P appropriately. Maybe it needs to be one operand to one over K, but for triangles, at least one operand to that there. But we don't have the analog results that if detection was easy in sparse random graphs, then it's easy in the web.
Yeah, that doesn't exist, and that's a big open problem. Basically, there's basically all of the results that we currently have in average case fine-grained complexity are on counting problems, and there's funny things where a lot of the reductions will break down basically exactly as you start to hit that threshold, where if you're trying to get your sparsity down and get that to work, suddenly your running time balloons to being the running time of the reduction itself balloons to being the size of the whole running time that you were trying to hit. And additionally, just if you grow K, right? The results don't just apply to constant K. They're sort of simplest to state because you can brush all the questions of exactly what the polylog is under the rug. But if you grow the K big enough that you're now expecting that there's only one clique, suddenly all the results break down and your running times don't match up anymore. So It would be awesome if we could do that, but at the moment we're like counting is where we're at, which is sort of one of the convenient things here because you guys seem pretty fine with counting. Like you know, don't seem to be just concerned with like getting the answer of like whether your query will return anything, but instead whatever broader questions about what's going on in your queries. These have been great questions. Thank you, by the way. All right, we are almost at the end, so I'm just going to jump ahead and tell you one fun fact before we get to the very end. And that fun fact is Nofar brought up zero triangle. And one thing I just want to highlight is that zero triangle is extremely hard. It's not just, so this is from Williams and Williams 13. Zero triangle is hard from negative triangle, which is equivalent to all pair shortest paths. And also it's hard from three-sum problem. Yes.
Sorry, what is zero triangle?
A zero triangle is
like a product or something.
Yeah, so zero triangle, you're given a graph with integer edge weights represented on log n bits, and you want to return true if there are 3 nodes that form a clique where the sum of their edge weights is 0. Is that also what you meant by zero triangle? Yeah, great. Yeah, and it turns out that this problem is really, really believably hard. So I mostly wanted to highlight this because if you can build your results off of zero triangle, like they're sort of especially well stated, or especially like solid. It's now noon, which I believe is the end of my time. So I should probably let you guys eat lunch.
Well, we should. Are there questions?
Was there anything else you would like to say? Maybe the next slide. I don't want you to end on this, like, let's go to lunch.
Yeah, so I think the thing I wanted to get as the sort of high level point is there exists this large number of fine-grained problems that we consider interesting. I'm going to go back to the earlier slide, as Nofar's problems. So there exist these large number of problems, and in fact, like many of the classic problems in fine-grained complexity show up. And the 2 things I want to highlight are, I think orthogonal vectors is likely to be very relevant to many of the lower bounds you want to get because it's often relevant for graph problems, and a lot of your problems are sort of underlyingly graph problems. I don't have immediate suggestions for how to get some lower bounds from it, but those might be able to get you some interesting lower bounds in especially cases where the underlying graph is sparse. So that's one thing I wanted to highlight. I wanted to highlight the average case problems are probably quite hard. And finally, that there exists this really large number of problems that you can base your hardness off of, and many of them have nice relationships to each other. Yes?
Yeah, one question about that. So you have this zero click problem at the bottom there. And you said for triangles, it's extremely believable, right?
Yes.
How do you feel about bigger clicks?
I also believe it for bigger cliques. It doesn't have like quite the same clear, reduction standing where it's hard from many other like well understood hypotheses.
Any implications?
So the problem is that negative k clique is actually it's hard from negative k clique. But basically, like the k-sum reductions break down, and there's not sort of an analog of all pair shortest paths. Like all pair shortest paths is equivalent to negative triangle. There's not really an analog for larger k. And to be explicit, the hypothesis for zero k clique is that it requires n to the k minus the low of 1 time. So you can't do better than exhaustive search. Yes.
What with the corresponding zero hyperclick conjecture?
Do we have something on that, Virginia?
It's harder than hyperclick.
Yeah. I don't think I have all that much to say about zero hyperclique, but
There's this nice paper where by Ryan and others where they do this losing weight by gaining edges.
oh right, and
Take a weighted problem in a hypergraph and make it into an unweighted problem in a hypergraph by increasing the error by a multiplicative of 2. And so in a sense, you can remove the weights by making it about, other
Just
types
about
of-
hyper.
It's about hyper.
yes.
Yeah, so if I understand correctly, over here you explained how to reduce deterministic click counting into probabilistic click counting over an Erdos-Renyi graph.
No, sorry, this was matrix multiplication.
Yes.
For clique counting, I don't know of any reduction that is quite this simple. But I could explain how to do it like offline.
Yeah, the part that confuses me is basically how do we get rid of the probability of being wrong? Because eventually, I suppose, like the final algorithm that we want is deterministic on any graph.
Great. Okay. Yeah. So I'll explain with this example, and then it like scales up. So let's say that we're like just wrong, but we're just wrong like 1/16 of the time, right? So our you can think of it as an adversary, right? Like we have some adversarial algorithm, and it's going to be wrong on exactly one of these. Let's say that's sort of the worst case, right? That like it's going to choose some instances, and these instances are going to be definitely only one of the following problems. Okay, so now if we've picked a uniformly random x and a uniformly random y, even if we're like wrong 1/16 of the time and we're sort of spread out as much as we possibly can be, it's still going to be the case that at most 1/4 of our instances, like at most 1/4 of random values of x and y can it like be wrong. So now we have a randomized algorithm. What we're going to do is we have our worst case a and b, and we're going to like pick an x and y, and then we can like pick many x and y and boost our probability there. So despite the fact that in this average case we're allowing it to be wrong on some inputs, when we do this reduction into the worst case, we're getting these randomized algorithms, but we're guaranteed on any possible worst case input that it's going to have a high probability of success.
But it's still not deterministic. You do not guarantee success.
Yeah, you're not guaranteed success. We're relying on the fact that we can have these random inputs that look uncorrelated with each other, and then combine them together in these useful ways. And that there's, as long as the probability of running too long or being wrong is sufficiently low, then we can get a high probability of success in the worst case.
You can also turn it into Las Vegas by checking.
Yeah.
You can check whether the solution is correct and keep it running, and that would be a Las Vegas.
How do you check the solution?
Randomized.
Yeah, for some problems.
For cliques, you can check if there's a key. Here now.
Consider if the problem you were trying to solve in the worst case was detecting a clique. You can turn a counting algorithm into a detection algorithm. So one thing you can do is basically you subdivide the graph at random, and then you continue searching only in the subsections of the graph that you've looked at. And so you can take some counting algorithm that might not have a perfect success rate, and then just sort of drill down until you get to an actual solution you've found. And obviously, there is still a case where you might not be able to convince yourself that there is a solution if the problem is if if you get really unlucky and you keep getting told there's no clique when there is a clique. But you can sort of do these like checking techniques as long as there's some way to like check your answer. Yes?
Does the S in S triangle stand for sparse or strong?
I assume sparse. Sparse. Yeah, the capital S in Seth stands for strong. So I understand why you have this question.
Is it stronger? S triangle than triangle?
S triangle. Well, so because it's M and in a dense, I guess I would say no, because I think triangle is like triangle as stated can contain the case where M is n squared here, but it need not be that case. No, I guess it is stronger. Yes, because of this, like it like M can be n squared, and then yes. So I believe it is stronger because it's sort of
triangle implies a sparse triangle, right? Because if you cannot do it in quadratic time, you also cannot do it in linear time with the number of edges.
Yes,
Triangle.
But the triangle, the version of triangle as stated wouldn't claim, for example, wouldn't make any claim about the case where there's a linear number of edges, right?
So I guess the thing is how you're quantifying the number of edges in hardness result, right? So if the hardness is like for all M or infinity value values of M, S triangle is hard, then that's a stronger thing than triangle.
Yeah, versus if they're, I guess maybe I like don't, yeah, maybe this is more of a question. So like, is S triangle a statement of for all sparsities, like for all possible sparsities or infinitely many sparsities, then you can't do this? Or is it that there exists some sparsity on which?
Well, the point was just you just need, it's just that it's phrased in terms of the number of edges, and so there are less edges than means it's not. I don't require it to be specifically sparse.
Okay, so I think what you're saying is that you would consider S triangle to hold if there existed any M for which it held.
If you can solve triangles in n squared time, it doesn't mean that you can solve S triangles in M time, just because M can be very small.
But the reverse is, if you can solve S triangle.
Yeah, but
basically, like, if it turned out that we like had a really fast algorithm for triangle finding, but only if the sparsity was exactly root n, or I don't know, n or something. So like, and so like we violated S triangle, but only on one specific sparsity. Would you consider that to violate the S triangle hypothesis? If S triangle holds if M is n to the 1.5, but not if n is n, would you consider S triangle to hold? No. Okay. Maybe that answered your question. It depends exactly what the quantifiers are, is the real answer.
Lunch. Let's thank Andrea and so please do come back